And a lot of the things we're going to talk about are not directly related to quantum field theory, but it'll keep popping up, so it's maybe a good way to think about this course. We'll often use the tools of quantum field theory, but the topics will really be drawn from condensed matter and things that are not elementary particle physics. Okay, so before we talk about actual course content, I wanted to go over some logistics. So I'm the instructor, of course, Ashwin Vishwanath, and the TF is Charles Xiong. He's operating the camera. So I think the camera will not be here every day, but there's at least one person registered for the course who couldn't make it and is presumably watching this right now, is it? Or
No.
later? Okay. Yeah. So one person who has a visa issue and is not here right now. Okay, so that's the so let me start by telling you a little bit how I plan to do the evaluation for this course. Maybe many of you are not taking it for credit, but if you are, so this is a graduate course, of course, so I'm trying to keep the evaluation as little as possible. The evaluation burden, certainly, and the idea is, of course, you're interested in the topics, and that's why you're in this course. And so a lot of the weight will be for a final project. So depending on the enrollment, I'm thinking about having people work in groups rather than individually. So maybe groups of 3. So of course, I guess the first question everyone has is, what if it's not divisible by 3, the number of people taking the course? But we'll worry about that later. So roughly groups of 3. So this should be a reading project, and I'll put up a set of topics. So it would be really great if it was also a research topic that you could come up with, something where you end up with a research question that maybe you don't quite answer, but at least you start making some progress. Okay, so I'll put up some topics, but if you want to come up with topics of your own, that would be great. Just come by and talk to me about it before you actually start work. Okay, and you can find your own groups, make your own groups. Okay, and the way to be evaluated is there's a report at the end of the course. I'll figure out the date. I'm still trying to find the right date, but it'll be after the reading period or towards the end of the reading period, and a short presentation. That'll be the way we'll try to evaluate this course. Okay, and then there'll be assignments. I'm thinking of 4 assignments, so once every 2 weeks roughly. So those will be the dates the assignments are due. And we're not going to grade the assignment in gory detail. It'll just be graded out of 10. Of course, if you don't submit it, you get 0. That's the sort of the baseline, but we won't really be looking at any details of how you go through your work, just whether you've done it reasonably well, and so on. So again, it's trying to keep the burden of evaluation as little as possible. Okay, and finally, there's 10% for participation, and again, don't worry too much about this 10%. It's just to make sure people show up and are engaged with the course. So if you absolutely don't attend any class, then you don't get that. But if you're here and you're engaged and you come to, if you're not very comfortable talking in class, you can come to office hours and discuss. Or feel free to discuss during the class, ask questions, or raise points and so on. I didn't anticipate this sort of size for the course. I think if everyone were to talk in this class, it may not be very easy to make progress, but I suspect the attendance will be slightly less in the next class. So that's kind of the evaluation. Any questions about that? Okay, so I got a few emails about what background is assumed for this course. So the main thing that you really need to know very well is quantum mechanics. And in some sense, you can say that what we're going to do is we're going to go from one particle quantum mechanics to many particle quantum mechanics. Again, what are the new phenomena that appear? And the big hurdle, of course, is to go from not knowing quantum mechanics to grappling with all of that physics. So if you really understand, or maybe not understand, but if you're comfortable using quantum mechanics, that will be the most important prerequisite. Statistical mechanics as well. So no, there's no assumption of previous course in QFT. I'm not even sure if that will be useful because we'll kind of take a different track over here, and yeah. So anyway, this is sort of the background. We will need a few things that you need to know just to understand the language in which this course is going to be taught. Okay, so again, there's no new physics in this. For example, second quantization. It would be very helpful if you knew second quantization, but if you don't, Charles is going to review this in the next few weeks. And similarly for path integrals, which will be in one of these sections. Hopefully those of you who don't know that, with a little bit of extra work, you can come up to speed. And if you are really uncomfortable at the end of 3 or 4 classes, it may be that you need some time to actually learn that stuff before taking the course. Okay, but I'm hoping that this will be a course more about concepts, and you'll be able to pick up the techniques that you need to, to follow the lectures as we go along. Okay, so it will be an experiment, let's say. So I'd like to have feedback from those people who don't have that background, whether they're actually able to follow what's going on in the class, or whether they're able to pick it up in real time as we go along. And I'll assign the first assignment will be pretty easy in the sense that it will really be about testing if you know this background material, or what you need to learn of this background material, so you'll have a sense that you're prepared for the rest of this class. Okay, so that's what I wanted to say about this, what you need. So I think there's going to be a question about when the section will be held. I think Charles had some options. Maybe you should send out a doodle poll with those options. I think that may be the best way to sort this out, rather than trying to get a show of hands or something like that. Yeah, that may take more time. Okay, so yeah. So before I get on with the rest of this. It would actually be helpful, I think, for me and maybe for everyone else in the class to get a sense for people's background and what you're interested in, what fields you come from. So if it's also, I think for this part of it, I need to know your names. So maybe can we go around the class? People kind of introduce themselves and maybe say a little bit about what your background is, if you're an undergrad or grad student. What your area is, just very briefly. I think we have quite a few people, but maybe you can go through everyone in about 10 minutes. Do you want to start?
Hello everyone, my name is Henry. I'm a 6th year PhD student here in the physics department. And my research is actually in self-assembly, but I'm also interested in quantum physics of matter as well.
Soft matter that you're also interested in. Okay.
Hi, my name is Matt. I'm a 2nd year. I'm working with Ashwin, working on symmetry protection.
We'll start with that. We're going to have some.
Hi, I'm Fuad. I'm actually from Germany. I did my Bachelor of Science and I will study for the fall.
I'm Dominic. I'm a G6 in the Viking group. I do AMF theory, working on trading materials.
I'm Mara and G6. I'm working on vertical energy quantum theories.
Victor, I'm a G5, and I work in string theory, science theory.
Yeah, how do we go? Maybe on the front. You want to start?
Okay, yeah. I'm Ruha, and I'm working with Ashwin. I'm the 2nd year graduate student.
How do we branch from there? Maybe go to the front. Go around. If you want to.
Yeah, I'm Henry as well. I'm a 1st year grad student. I like condensed matter theory, but don't really know more than that.
I hope you still like it at the end of this course.
My name is Peter. Actually, I am from China and I am visiting here. I will stay here for several months and I'm very interested in topological aspects of condensed matter physics. So I attended this course. Will that be okay?
I'm Scott, I'm a G4. I work on conformal field theory and string theory.
Hi, I'm Minja. I'm G5 and I work on CFD and string theory.
I'm Visha, I'm a postdoc. Heinrich in Transmedics.
I'm Carrie, I'm a G2. I do Pheno and general DSM physics.
I'm a Hofi, I'm a J3, and I work on geophysics and particle physics.
I'm Rachel. I'm a G1 student in applied physics and I work on superconductors.
I'm Wuhan. I'm a G2. I'm working on energy technology.
I'm Tom. I'm an experimentalist working in van der Waals materials and quantum Hall effects.
Hi, I'm Sushruth. I'm a fourth year undergrad at MIT. I'm interested in general aspects of quantum theory.
Hi, I'm Chunker. I'm also a fourth year at MIT. Interested in condensed matter theory and quantum information.
I'm a fourth year grad student at MIT, but I work with Eugene Delner here at Everything Collaborative.
So what is the name again?
Kushal. I'm Michael. I'm also a fourth year grad student at MIT, and I work in condensed matter theory.
I'm Andrew. I'm a G1. I'm a condensed matter experiment in 2D electron gases.
I'm Alex. I'm a G1, and I'm interested in non-reducible aspects of quantum field theory.
I'm Blake in applied physics, and I'm doing materials theory.
I'm Harvey, G1 doing condensed matter theory, probably looking at field.
I'm Will, a special student here, and I'm studying topological metamaterials.
I'm Zoe. I'm in condensed matter experiment, G2.
I'm Jenny. I'm a first year at MIT.
My name is Chen Hao. I'm a researcher in the Gauss Group and Center of Mathematical Sciences and Applications, and I work on topics in spin field.
I'm Sean. I'm a G2. I work on electrical molecules with John Doe.
I'm Yisha. I'm G2 and also working on the laser cooling of molecules in both.
I'm Sean. I'm a grad student. I work on the computational physics and material science.
I'm Jimmy. I'm a sophomore at the college, and I'm interested in statistical physics.
I'm Abby. I'm a junior at the college, and I'm also interested in statistical physics.
I'm Roland. I'm a G1 student. I'm an experimentalist and working on National Research Center.
I'm Shuyu. I'm a German student in physics and also interested in condensed matter theory.
I'm Barbara. I'm a G1. I'm interested in energy formal theory.
I'm John, MIT second year student working on condensed matter theory.
I'm Nishargo. I'm a senior here, and I'm taking this to gain exposure to condensed matter.
I'm Cameron. I'm a senior here as well. I'm interested in topological materials.
I'm Davis. I'm a senior at college. I've taken some courses in QFT, and I want to see it on the lattice.
I'm Yukiga by Harry. I'm a G3 and Misha Lukin's group. I primarily work on AMO experiment on the side of quantum sensing and many-body physics, but at the same time I also have an interest on topology and nondimensional.
I'm Yifei. I'm a postdoc in condensed matter theory.
Okay, so did you complete?
Yeah.
Yes, you want to introduce yourself?
Oh, yeah, hi. I'm Jun Hee, G6, grad student in Misha's Lucas group. I'm an experimentalist working on high density strongly interacting spin oscillators.
Chairs on that side. Okay. Okay, so thanks. That was actually went better than I expected. So let me tell you a little bit of what I plan to do in this course, and what the outline of this course is. So I think some of you are trying to decide whether you want to take this course for credit or not. So maybe that will help you. I think also it will be good to, at the beginning of the course, get a sense for where we'll be going and the bigger picture of what's happening. So really, like I told you before, we're going to go from one particle quantum mechanics, which is what you're taught in your quantum mechanics course, to systems of many particles. Okay, and there's lots of interesting physics that comes out, and in some sense, the big discovery, if you like, is that many particles are not in some additive way related to the one particle physics. Okay, there's really, the whole is much more than the sum of the parts, so if you like, there's some emergence. So I'll give you some examples as we go along, and that requires its own kind of laws and physical principles, which have sort of been discovered independently in different areas. Okay, and we will kind of focus on the condensed matter version of this, but a lot of the similar physics has been independently figured out in the high energy field theory side. Okay, so often we'll work with extremely simple models, and it'll be kind of a shock that many of these models that are so easy to describe are actually not understood. Okay, so it's a little bit like number theory. You can pose anyone can pose a problem that take years to solve, or maybe unsolvable. So the simplest quantum mechanical system you can think of is a spin a half. Okay, so the spins are either up or down, just two states. You can also think of it as being a site empty or occupied, so we'll often think of this as particles being present or not. So the modern, or at least the fashionable way of talking about this is a qubit. It's a 0 or 1, but it's quantum mechanical. You can have superpositions, and we're going to ask what happens when you put many of these things together with some interactions between them. Yeah, so another kind of physical setting these qubits could refer to, it could be different positions of an atom. Okay, so this is ice. It's a slightly different structure from the ice that you have at ambient pressure, but so this structure of ice, of course, there are these oxygen atoms, but you also have hydrogen, and it turns out that the hydrogen have to sit between the oxygen atoms, but there are two positions where they can sit. And so you can imagine the configuration of ice having these variables that are 0 or 1 depending on where the hydrogen sits. Okay, so in fact, there's a lot of different configurations of the hydrogens that's present for a given structure of ice. And it turns out that's very important for the thermodynamics of ice, for its properties. And if you go to low temperatures where quantum mechanics becomes very important, you should think of that as a quantum two-level system. Okay, so we'll come back to this later. There's interesting physics that happens in this particular quantum system. Okay, so to give you an example of a question that I can pose very easily, but nobody knows the answer to, imagine that you take these qubits or spin 1/2 particles on a lattice. This is actually realized in many materials. You have a lattice of atoms, and the spin is really the electron spin. Okay, and the electron spin has two states, up or down, but they interact. Okay, and the interaction is, roughly speaking, given by this Hamiltonian. Spins on neighboring sites, their spin vectors like to be in opposite directions. That's what this means. S dot S with a positive coefficient J, that's an antiferromagnet. If the sign of J was reversed, if this was a ferromagnet, all the spins like to point in the same direction. It's very easy to figure out the ground state of the system. And so if you like, the challenge is flip the sign of J. You go from all the spins pointing up to them wanting to be anti-parallel on neighboring sites. And there are many ways of doing that. And they're actually quantum spins. You can't just think of them as being up or down. They could be in a more interesting or complicated state. Okay, so with this simple Hamiltonian, this is what it looks like in terms of the Pauli operators, 2x2 matrices. It's just this coupling. You can easily formulate this question. It's relevant to materials, relevant to magnetism. But it's been decades, and still people haven't figured out what is the ground state of the system. And so every conceivable state has been proposed, but they all have problems in interpretation. And really one of the challenges for theory is, can we come up with reliable ways of figuring out ground states? If we can't do that, at least can we come up with scenarios? These are the different possible ground states. Can we describe their properties? What are their signatures? And you can either go to experiment and see if those signatures are being realized, or you can go to numerical simulations, numerical experiments if you like, and see if those signatures are being realized. And to date, for various reasons, these different states that have been proposed, from rather mundane states, really just spins pointing in particular directions, really having a very classical feel to them, to things that are very quantum mechanical. For example, this state, current favorite is this particular state. It's called a U1 Dirac spin liquid. The effective theory that describes this phase, according to that scenario, is really quantum electrodynamics. Okay, the same theory that describes electrons and photons in 3 dimensions. Of course, this is a 2-dimensional system. Reduce it by 1 dimension. That's the effective description. Of course, those fermions and photons are in some complicated way related to these physical spin degrees of freedom. But that's kind of the range of physical theories that have been proposed to describe this particular system. And so we'll see that one of the very useful things we can do is to understand what are the low energy properties, what are the essential features of these different kinds of states. And that's something we'll go through in sequence in this course. Okay, we'll start with the very simplest ones, the magnetically ordered ones, and then work our way to gauge theories. So for example, the Z2 spin liquid is described by gauge theory, and this is described by an even more complicated physics. There's a gauge theory, but it's also coupled to low energy fermions. Okay, so I don't know if we'll get to that point, but we'll certainly talk about gauge theories. Okay, so so the aim, one important aim is what are the different scenarios, right? What are the different kinds of qualitatively different physics that you could come up with? So this may be familiar to some of you, but it may be good to review this, for if you have not been exposed to it before. So really one of the new things that appears when you have many particles, which you don't have any analog, when you have a single particle, is that you get phases of matter. Okay, so we're all told that there are 3 or 4 phases of matter. This is kind of a typical phase diagram that you might see. And these phases, if you move around in a phase, nothing much happens. Properties change. If you move around the phase of gas phase, maybe the density changes as you change the pressure and temperature, but nothing drastic happens, except when you cross these phase transitions. You cross a condensation transition, or I guess this is sublimation. When you cross these phase transitions, something drastic happens, and that really gives you the boundaries for the phases of matter. Okay, so if you define your phase of matter as something that's completely enclosed by these phase transitions, a very obvious question to ask is, what are the different phases of matter present? Okay, so before you go in and list the detailed properties of the gas, maybe you just want to know what are the qualitatively different behaviors that can be exhibited. Okay, so a solid, of course, has some qualitatively different features from a liquid. You can apply a shear stress, for example, and it will resist that, unlike a liquid. So that's sort of the 0th order program, and that's a lot of what we'll do in the course. Okay, so fortunately, the physics of quantum systems, and in fact, even more generally, the physics of even classical systems is much more rich than you would expect from just this phase diagram. Okay, so this is just the starting point, but already there's something kind of interesting over here, which is you can ask the question: are these really different phases? For example, is the gas and the liquid really different? We know they differ a lot in terms of their density. Ambient pressure, the liquid water is 1,000 times more dense than a gas. So you can't be confused about which is the liquid and which is the gas, right? But in terms of actual qualitative difference, is there some difference? And in fact, if you look at this phase diagram in a bigger range of axes, increase the temperature, increase the pressure, what you discover is actually the phase boundary between the liquid and the gas terminates. It actually ends somewhere. This is called the critical point. And if you go beyond that, there's really no distinction between the two. Okay, so remember, the distinction is really just density. It's a quantitative distinction. It's a factor of 1,000 over here. But as you increase the temperature and go up in pressure to be on this line, the difference in density becomes smaller and smaller and eventually vanishes beyond this point. Okay, so you can take a path. You can change parameters so that you go from something that's definitely a gas to something that's definitely a liquid without ever encountering a phase transition. Okay, so then of course these two categories are not that well defined. You have to say where along this trajectory did you switch, and everything is smooth along this trajectory. Okay, so this thing of classifying phases is a bit more tricky than you might first expect. You may then begin to doubt whether this line actually goes on forever. Maybe if you go to really high pressures and temperatures, you can smoothly go between a liquid and a solid. Okay, or can you? Right? But it turns out that's actually not possible. That line does go on forever. And there's a way to make a qualitative distinction between these two. For example, the response that I just spoke about, or actually most solids are crystals. Okay, so they have a very periodic array, periodic arrangement of atoms, and you can actually use that periodicity to sharply define the distinction between a liquid and a solid. Okay, so that boundary really goes on forever. Okay, so it's a little bit like this, this kind of game that, back in the days when people actually had a physical game, right? You would move these squares around, and you're supposed to go from this sequence of numbers to this one over here, okay, with just the last two numbers exchanged. And the question is, can you do that in a smooth way? You're only allowed to move into the empty square or not. Okay, so apparently when this game was invented, there was a big prize given to anyone who could do this. Okay, and of course the inventor knew that you could never do this. It's pretty confident, so gave this big prize. So you can think of this as kind of our problem of classifying phases, right? Are these two sequences connected smoothly, or do you have to go through a phase transition? So if you break this and reassemble the pieces, that's the phase transition. But you can always do that to connect two sequences. Okay, and the way you can tell you cannot do this is you can find an invariant. You can find a number, 0 or 1, that you can assign to each sequence of each sequence, and you can show that that number is not changed by any of these moves. Okay, so there's some sort of parity that you can assign. Maybe that's a good exercise. Come up with a parity that which will be an invariant of these moves, and you can show that that parity is 0 for this one and, for example, 1 for that. Okay, so there's no way to go between the two. We want the analog of that for phases of matter. Okay, so we want the analog of a set of numbers. Ideally, this is sort of the dream, that we identify all such characteristics, which, if you tell me a particular state of matter and measure all of these characteristics, I can completely specify what else can be continuously connected and what cannot. Okay, so that's kind of the program in trying to classify the phases of matter, and actually we are nowhere close to completing that. Okay, so in fact, people back in the day, they thought they had a solution to this. They thought they had figured out all these kind of parity things for states of matter, but in fact we learned that was incomplete, and there's more to it than that. But I can tell you what the idea was. Let's say in the 70s, maybe they didn't actually phrase it like this, but the idea was that you get different states of matter because you break symmetry. And if two states of matter have the same symmetry, it may not be obvious, but there's some way to connect them. Roughly speaking, that was the thought. So for example, we talked about a crystal. There's a periodic arrangement of atoms in a crystal that breaks the homogeneity of space. You pick a particular position for your atoms. In a liquid, on the other hand, if you wait for a while, every position in space will be visited by molecules. It will look the same as any other position. In a crystal, no matter how long you wait, you have a certain rigid crystal. It doesn't, there are positions where there are atoms, there are others where there are voids. It kind of breaks the translation symmetry, if you like, this way. Yeah, ferromagnet also is a symmetry breaking state. The electron spins pick a direction. There are others which are a little less obvious that they're symmetry breaking. Superfluids, for example, are symmetry breaking states. They can be described just like these other states. There's an order parameter. It's a little bit harder to put your finger on what that order parameter is. Okay, we don't have as good an intuition for what that order parameter is. Okay, but instead, the way in which you identify a superfluid, it's much like how you identify a solid. Okay, people knew there were solids long before they figured out that they were actually crystals, right, with periodic arrangements of atoms. Periodic arrangement of the atom, you can see in X-ray diffraction. So the analog of the spin being along a certain direction for a ferromagnet, it's actually the Fourier component of the density in a crystal. Okay, so there's periodic arrangement, and if you do something like X-ray scattering, you pick out this periodicity in these peaks, you get these so-called Bragg peaks. That's really the order parameter. Okay, but people knew there were solids before they did X-ray scattering. X-ray scattering was at the beginning of the 20th century. Partly you had hints because you had these